Now I would like to generalize all this subject, the Cohen Kuznetsov Zagier differential operators, all these exercises which we formulate about modular forms and differential operators, about ranking Cohen brackets, I would like to generalize all this stuff to the case of modular forms, Jacobi modular forms, in many variables. So let me show how we can change the notion without any changes in the proof. We start, in the case of modular form, with trivial lattice. So when we consider the modular form, our lattice is trivial. This is 0. Now we consider any positive definite lattice of rank n0, and the variable z, calligraphic z, belongs to the complexification of our lattice. So this is a complex vector of rank n0. In the case of the trivial lattice 0, the modular differential operator has this form. This is d plus 2k g2, the operator of multiplication by the quasi-modular Eisenstein series G2. In the case of Jacobi modular forms in many variables, we have to change the differential operator d by the heat operator h with the corresponding normalization. And we got the modular differential operator in the case of Jacobi form in many variables. So what changes we have to make in all formulas? First of all, we have to change the differential operator d by the heat operator h, and we have to change the weight k by the weight k minus n0 over 2. n0 over 2, this is the singular weight. So we can define the following differential operator EKNH. This is the original operator with corresponding changes. So we change k and d by h. But in the proof of the corresponding theorem, we have to use only this congruence, which is still true for the heat operator, because the main modular part of the heat operator is the same. This is 1 over 2 pi I delta over delta tau. So this operator EKNH is a modular differential operator. This operator acts on the space of Jacobi modular form of weight k. And then certainly this operator changes the weight from k to k plus 2n. Like in the previous case, we can construct the power series of this operator. Certainly we have to cancel the numerator. Then after that, we have the convolution of the two power series, the exponential function of the quasi-modular Eisenstein series, and this variant of the Cohen Kuznetsov Zagier operator. We have to put here h instead of d, and we have to change also the weight. Please be careful that the weight of modular form is greater or equal to n0 over 2. This is certainly true for all holomorphic modular form. We have proved this result when we studied the Weyl representation. Now, like in the previous case, we have the following diagram which explain the nature of our operator. First of all, we construct the Jacobi form of weight k and index 0. This is a power series of usual Jacobi forms. We construct this Jacobi form using the modular differential operator. Then we take the automorphic correction, which works very well in the case of many variables, and the result is the modular operator which we need. So we proved the following theorem. Let phi be a modular form, holomorphic modular form of weight k for the lattice L of rank n0 over 2. H will be the heat operator. Then the following function, depending on tau, that, the calligraphic z, belong to the complexification of the lattice L, and small z is the usual complex number. Then this function is a Jacobi type form of weight k for the lattice L and index 1. So this result which we have, and the proof is identical to our proof of the Cohen Kuznetsov Zagier theorem. Maybe I would like to remind you then this fact, then we have a Jacobi type form, means then the corresponding function satisfies the following functional equation. So we have the usual functional equation of Jacobi form, then Jacobi type part, and the result has weight k, and we have two Jacobi factor. The first, this is the factor of Jacobi form for the lattice L, pi I c calligraphic z to the square c tau plus d, times the factor of Jacobi type, 2 pi I c z to the square c tau plus d, and our function. And we have this functional equation for any a, b, c, d in a cell to that. In particular, some remarks. If L is the trivial lattice, then this theorem, the last theorem, is equivalent to the Cohen Kuznetsov Zagier result theorem. Then I can formulate the same series of exercises in the case of Jacobi modular forms. So please define a generalization of Rankin-Cohen bracket for two Jacobi forms for different lattices. I don't see any problem with this. So we have two Jacobi forms for two different lattices. You can construct the corresponding functions, and like in the case of trivial lattices, you have to analyze the product what is it? It will be Jacobi type form. Jacobi type form of weight, I hope, K plus L for the lattice, the direct sum L and M, and index 0. So taking the Taylor expansion in Z, you can get the generalization of Rankin-Cohen brackets. In this case. Then you can analyze the bracket with G2. Let me write it like this. Phi and G2. Then you can analyze certainly the case of half integral weight. In particular, you can consider the Jacobi theta series constructed by Jacobi functions, Jacobi theta, tau z. You can construct a lot of nice examples. And you can prove a lot of nice theorems. Then I can put a question about K, which are smaller than n0 over 2. Why this case is important? Because in this case, we could have a pole in gamma function. So this question is very similar to the question 4 I put for modular forms. So you see, we can formulate a lot of interesting research questions. Some of them are simple, some of them are more complicated. So I would like to finish my course and this lecture with the following proposition. If this subject is interesting for you, please ask for master and PhD subjects. I am sure that we can find 10, 12, 15 different subjects for different students. I hope for the possible contacts with you.